All right. So that characteristic of gradients we just talked about, pointing in the direction of quickest increase or being perpendicular to level curves, is actually going to give us one more cool feature. Guy, you got to get off this book. So I'm going to talk through why the equation I'm about to write down is true so that hopefully it's easier for you to remember. But when we were drawing these pictures, I kind of made the argument that if the gradient vector is pointing in the direction of quickest increase, it's going to be perpendicular to the level curves. And that was when we were talking about z equal to f of xy. So if we're thinking about a surface g of x, y, z equal to some constant, that's going to be a level surface. So it's kind of like if you had some g of x, y, z and then set it equal to a number, same thing as we do to attain these level curves, but for a function that depends on z as well. But if we have a surface g of x, y, z, the vector grad g is going to be perpendicular / normal to the surface at every point. Just like it was perpendicular to level curves, it should be perpendicular to this level surface, g equal to a constant number. It's not going to be perpendicular to any random g of x, y, z. It's only perpendicular to ones that are set equal to constants. But if it's perpendicular / normal to the surface, then we can construct tangent planes. To make a plane, all you need is a normal vector and a point. So to make one of these tangent planes, we're going to use the normal vector that's actually perpendicular to the surface itself and a point. At any point x0, y0, z0, it's going to be given by this equation. Grad g evaluated at x0, y0, z0, dotted with x minus x0, y minus y0, z minus z0 equal to 0. What that really is writing is that I just want the x component there or here. We'll do it like this. This really just turns into that a times x minus x0 plus b times y minus y0 plus c times z minus z0 that you're so used to seeing, except for grad g is just giving us those a, b, and c components evaluated at that point. I should be really careful with how I write this down. I don't want y'all to ever forget plugging in the point. All right. So that's how we can construct tangent planes. We'll do an example that does that. But just so you know, also, we can parameterize the line along the normal vector. So kind of going back to this picture, maybe I'm right here and I just made my tangent plane using a normal vector. We could make a parametric equation for a line through a vector. We learned how to do that in the first section of class, and this is just writing that equation down for us. However you want to write it is fine. I'm going to go ahead and write it like this. Those different components, again, where grad g evaluated at the point x0, y0, z0 is giving us those a, b, c values that we always plug in. So let's go ahead and do an example of this. Wait, first let's make sure I didn't go over 5 minutes. I did. I feel like I can do this quickly though. All right, so we're going to find the tangent plane to the surface x squared y plus y squared z plus z squared x equal to 5 at the point 1 minus 1, 2. All right, so first we just have to make sure to read off this, the function of 3 variables that we actually care about, set equal to a constant. So our g is that x squared y plus y squared z plus z squared x. And we're looking for the tangent plane to the level surface of this function set equal to 5. And I'm going to look at all my partial derivatives. So dg dx is 2xy plus 0 plus z squared. dg dy is x squared plus 2yz plus 0. And dg dz is 0 plus y squared plus 2zx. And so my gradient is just made up of those 3 components, 2xy plus z squared, x squared plus 2yz, y squared plus 2zx. And evaluated at the specific point I care about, 1 minus 1, 2, I've got 2 times 1 times minus 1 is minus 2, plus 2 squared is 4, so that's 2. 1 squared is 1, plus 2 times minus 1 times 2 is minus 4. It's minus 3. Minus 1 squared is 1, plus 2 times 2 times 1 is 4. So that's going to give me 5. And so my tangent plane is going to have 0 equal to something times x minus the point I'm dealing with, plus something times y minus the point I'm dealing with, plus something times z minus the point I'm dealing with. So these values right here came from the original point I was given up there. And then the slopes on my plane come from my gradient vector. Oops. I'm just going to try to mark these really carefully so that we know where everything came from. And so that's the tangent plane. And then if we wanted to, we could also say that the normal line is, let's see, I start with my points and then I just add t times the slope. Oops, keep forgetting about that minus sign. And then 2 plus 5t. And I'm going to, again, underline the slopes that come from the gradient vector and squiggly line the points that come from the point we're looking at. And that's how you can use gradients to find tangent planes or normal lines. add that to the problem statement. Just remember that the gradient vector, you do have to plug in that point to get the specific value. If you start to create a plane equation and end up with x, y's, and z's in your slopes, you're going to get like z squared in a component. You know that that shouldn't show up, and that tells you that something went wrong. So always evaluate it at a point before you plug it in.